So let's go ahead and begin with hypothesis test for means. It's very, very similar to a hypothesis test for proportions, with the exception that instead of using a z-test like we did for proportions, we're going to go ahead and use a t-test for means. Okay, and remember the reason we're using a t-test is because we're rarely given the standard deviation of the population, and that's what's required for a z-test for means. So we're just going to go ahead and stick with the t-test. Okay, so we're going to go ahead and use is the name of the test, one sample, because right now we're only going to use one sample. One sample t-test for means. Okay, and remember, a t-test requires degrees of freedom, right? And the degrees of freedom formula was just n, the sample size minus 1. That has not changed from when we did confidence intervals for means, right? The t confidence interval for means. All right. Now, just like with a z-test, we're going to have conditions. Okay, and these conditions are just the same, kind of the same ones that we use for proportions, right? The first condition was that we have a random sample. Second condition is that our sample size is less than 10% of our population size. Again, that hasn't changed. The one that differs a little bit is the third condition, right? The condition for normality. So remember that in the third condition for confidence interval for means, we had one of three things happening. One, we either had the population distribution, okay, to be normal. So the population distribution is approximately normal or is normal. Okay. And if that wasn't stated, okay, we also know that by the CLT, the central limit theorem, if your sample size is greater than or equal to 30, we also have, or we can also assume, a normally distributed population. However, if one of these two cases didn't hold, okay, then we'd have to go to the third alternative, right? So if n is less than 30, and nothing is said about the population distribution, then what we're going to have to do is check the sample data. For normality. Okay, and by checking sample data for normality, we're just going to check that it's not too skewed or that there's no extreme outliers, so that way we can assume it comes from a normally distributed population. And of course, we proceed with caution. All right, so keep in mind that we still have conditions to do, and just like we still have conditions to do, we still have a procedure. Okay, first step in the procedure, just like the test for proportions, is to state your hypothesis. So state ho, ha, and of course your population characteristic, right? Now here, since we're testing means, this population characteristic is no longer P, right? We're not testing for proportions anymore, we're testing for means. So this population characteristic now is mu, okay? Second thing is we're gonna go ahead and check conditions. So we know in this step we have 3, right? And if it is that we're going to go ahead and check for conditions and your sample size is less than 30, you're going to have to draw the box plot or the bar graph, the histogram, or whatever it is that you use to show that it's an approximately normal distribution or that it's not too heavily skewed, okay? So let me write that down. Draw a graphical display. If needed. Okay. Third condition is, of course, our do condition. So that means we have to name the test. Remember, naming the test is crucial, or else you won't get credit, especially if you're doing it all on the calculator. So name the test and do work, and show work. Okay. And then the last step, of course, is your conclusion, where you reject the null hypothesis or fail to reject the null hypothesis. Right, and for the conclusion, remember, you're going to test your p-value and compare it to your significance level. And we should remember the symbol for significance level, and that is going to be alpha. All right, it's the same thing as with proportions. If your p-value is lower than alpha, right? If your p-value is lower than alpha, you're going to reject the null. If your p-value is greater than alpha, you're going to fail to reject the null hypothesis. Okay, so just keep that in mind as you're working through problems. All right, just to help you out a little bit, we're going to do one quick example. All right, give me 1 second here. Where did I leave it? There it is. All right, so in this particular example, we're talking about the level of dissolved oxygen. All right, so the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along the stream. Here are the results in milligrams per liter. Okay, now it says dissolved oxygen levels before 5 milligrams per liter puts aquatic life at risk. Do we have convincing evidence at the 5% significance level that aquatic life in the stream is at risk? All right. So in this example, just like any example, it's important to identify anything that is important. All right. First thing is notice the 15. All right. They have 15 randomly chosen locations. So that 15 is talking about our sample size. We have a sample of 15 locations along the stream, right? Now, here they tell us what value we're going to go ahead and use in our null hypothesis, right? It's the one we're testing. So just like with proportions where we use P naught for the value we're testing in our null hypothesis, here we're going to go ahead and use mu naught, okay, the value we're testing in our null hypothesis, which is going to be 5 milligrams per liter. Okay. And then, of course, the 5% significance level. Like I said, we should all know the symbol for significance level. It's that fish-looking thing. It's called alpha. So alpha is equal to 0.05. And that's about all the data that they give us, okay, in the problem itself. Now, they do give us all of these numbers. And, of course, when they give us a list of numbers, we go to our calculator to type them in. All right, so first things first, let's go ahead and go to our list and spreadsheets. Okay, and these are all talking about DO levels, so I'm just going to put DO. And then I'll go ahead and type them in. 4.53, 5.04, 3.29, 5.23, 4.13. I encourage you to do this as well, so that way you can practice. 5.42, 6.38, 4.01, 4.66, 2.87, 5.73, and 5.55. Let me just make sure I have 15 values. I do. Excellent. Okay, let me go ahead and put this aside. I have my data in, and then from this data, we'll be able to get all of the information that we need. Okay, but let's just leave that aside for now. Okay, so let's go ahead and start with the procedure. Notice that they ask for convincing evidence, right? So whenever they ask for convincing evidence, you should know I'm going to carry out a hypothesis test. Okay, since you don't have percentage values, these are not percentage values. We're not doing a test for proportions. We're doing a test for means. So first step is, of course, to state your hypothesis. The null, the alternative, and to state whatever your population characteristic means. Okay, so in this case, right, your null hypothesis is mu equals to the value stated, right, the 5 milligrams. Okay, and for your alternative hypothesis, notice it says dissolved oxygen levels below 5 milligrams puts aquatic life at risk. And we're trying to see if there's convincing evidence that aquatic life is in the stream is at risk. So then your alternative hypothesis is mu is less than 5 milligrams per liter. Okay, where mu, right, is talking about the true mean. Okay, the true mean level of dissolved oxygen, it's right here. Of dissolved oxygen Okay, the true mean level of dissolved oxygen, okay, in the stream. Oops. Okay, and we have everything in step 1. All right. Second step, conditions. First condition is random sample. In the problem, they say we have 15 randomly selected locations. So the first one, there's 15 randomly selected locations. Okay. The second thing is the sample size has to be less than 10%, right? But we're really just sampling from a stream, right? So you can actually sample an infinite number of locations. So you really don't have to worry about the less than 10% here. So we can just write the following. Okay, there is an infinite number of locations to sample from in the stream. So that's that. Okay. And the last condition is the one for normality, right? To see if we're able to use that t-distribution. And in this case, notice that it says nothing about this being from a normally distributed population, right? Our sample size is 15, so we can't use the CLT either, meaning we're going to have to go ahead and check the data to make sure that it's not too skewed. All right, so that's where our calculator comes in. All right, so on the calculator, of course, we go ahead and have our data, which we should have already typed in. And to check a graphical display, remember that we just go to graphs. I'm sorry, not graphs. I'm thinking pre-calc. Okay, so for a graphical display, we should go to Control Doc and Data and Statistics. At the bottom, of course, you're going to go ahead and click to add your variable. And here we see a dot plot. It seems pretty spread out. But of course, it's easier to draw a box plot. So let's look at the box plot. All right, and notice from the box plot that it's not too bad. It doesn't look too skewed. There's no extreme outliers either. Remember, they would be noted by dots over here at the end. So everything looks good. Okay, I'm going to go ahead and plot these values on my paper to show the following. So I'm going to go ahead and draw my title label tick tick. Remember, that's important. Okay, here we're talking about the DO level. All right, let me see what my minimum was, so that way I can just write the essential numbers. So we have the minimum to be 2.87. I'm going to go ahead and write 2.87. Okay, that's my minimum. Okay, actually I should probably write a number at 3. 3 and 4, 5, 6, and 7. I'll write those numbers. All right, my Q1 is 4.13, which is about right here. Okay, my median is 4.83, which is about over here. My Q3 is 5.55, so that's right here in the middle. And then my max is going to be 6.38, which is about over here. All right, so all I have to do is draw my box plot. And there you go. All right, there's your box plot. So since it doesn't look too bad, we can go ahead and write the following. Okay. Since the data shows no extreme skewness or outliers, we will assume, okay, it comes from a normally distributed population. Okay, so then we'll go ahead and leave it like that. We have our data. Okay, we showed that there was no apparent skewness or extreme skewness or outliers, so we can go ahead and proceed with our test. All right, so that leads us to the third step. The third step is to do. Okay, they only collected one sample of 15, right? The sample size was 15. They only did this one, so this is called a one sample Since we're working with means and have no population standard deviation, this is going to be a t-test. One sample t-test for means. Okay, one sample t-test for means. And of course, we have to state the degrees of freedom. Okay, the degrees of freedom is your sample size minus 1. In this case, our sample size is 15, so 15 minus 1 is 14. Okay, and in fact, on the calculator, it should give us the degrees of freedom, in case you forget to write that down. All right, so going back to our calculator, we go ahead and show our work. Right, remember that we're not going to do this by hand, we're going to do the calculator, so we'll go ahead and add another page, this time to a calculator page. Okay, under menu, statistics, and stats test, just like we did for the one sample z-test, okay, we have the t-test here. For this one, we are going to use the t-test one. Okay, so we click on t-test, and then it asks you, do you have data or do you have the statistics? In this case, we have data. By statistics, they mean do you have the sample mean, the sample standard deviation given, and so on and so forth. We don't, we just have data. So we're going to click OK. And then it asks you what your mu naught is, right? Our mu naught is a value coming from our null hypothesis, which is 5. The list that we're using is, of course, DO. Frequency list, leave it alone. And then we state our alternative hypothesis. Our alternative hypothesis was that mu was less than 5. So we're going to choose that one. Okay, we click OK, and it gives everything to us, meaning all we have to do at this point is go ahead and write it down. Okay, so let me move this out of the way so we can write it down. This is not working very well. All right, there we go. Okay, so first thing you need to write is, of course, your t-value. Your t-value is going to be negative 0.942556. Okay, your p-value, which is what you're going to use to reject or fail to reject, right, is going to be 0.180945. Okay. All right. And then we have our degrees of freedom. So again, if you forget the degrees of freedom in the name, you have it here. So degrees of freedom is 14. Your sample mean is going to be 4.77133. Okay. Sample standard deviation is going to equal to 0.939596. And then, of course, our sample size is going to equal to 15. All right, so if we think about it on our t distribution, right, this is going to be t with degrees of freedom of 14, okay? And just like a standardized normal curve, this value is just going to be the true mean. It's going to be 0 in this case, all right? So our t value is negative, meaning it's going to be to the left of 0. If this is 1, okay, your t value is right here. It's going to be t. Okay, and since we're testing a hypothesis, right, where it's less than, we're shading to the left. Okay, and this t value was negative 0.942556. This shaded area is, of course, your p-value, which is 0.180945. So the probability of you getting such a sample size, given that 5 is the true mean, so in a non-normal, in a non-standardized t-curve, this is 5. Okay, the probability of you getting this sample, this particular sample, mean of 4.77 is going to be 0.180945. All right, so after you have all of this data, compare it to your p-value, okay, or to your significance level. So the p-value equal to 0.180945. Our significance level in this case was 0.05, and we see that it's greater. Okay, so that means we're going to fail to reject. Okay, so our conclusion, last step, since 0945 is greater than 0.05, which is our significance level, okay, we fail to reject the null hypothesis. Okay, so there is convincing evidence, or there is not convincing evidence, I'm sorry. That aquatic life is at risk in this chain. Okay, We could have also put that the true mean level of dissolved oxygen in the stream is less than 5 milligrams per liter. Okay, so keep that in mind.